So if you think about the block diagram of the BCD adder, the block diagram of the BCD adder looks something like this. It basically is similar to the binary adder. Only difference between the binary adder and the BCD adder is it takes in two 4-bit numbers which are essentially BCD numbers. So again, when things like these are given to you, you don't have to test, right? We will assume that the inputs, the user who's using the chip will take the pain of figuring out whether the inputs are a BCD or not, right? So you have these two numbers coming in, A and B, right? And you have a CN coming in, right? And so your output is going to be S3, S2, S1, S0. Again, this is a BCD number, right? And you have C out. So remember, A and B and S all are BCD, right? So if you want to implement a 4-bit say BCD adder, so how would a 4-digit BCD adder? So remember, a 4-digit BCD number, let's consider 1, 2, 3, 4. How would you write this in BCD? In BCD, each and every digit becomes 4 bits, right? So it becomes 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 0, right? So this is how you would write 1, 2, 3, 4 in encoded in BCD, right? And so how would you implement? Suppose I want to implement a 4-digit BCD adder. Then what I'll take is I'll individually implement each and every 4 bits as a BCD adder and use the C out of the first. So for example, what will happen is that this will be one BCD adder, right? And I'll take the C out of this adder and push it into the CN of the next adder, right? And so on and so forth. So again, designing something hierarchical makes it very easy to blow this up to a larger bit length or anything. So always remember when you're doing designs henceforth, keep in mind that this is what you want to do. You don't want to keep designing K-maps or QM method or whatever you have, or some online technique to simplify your circuits, but rather start thinking in terms of blocks, because when you're actually going to implement this in real life, these chips are readily available in the market. So you don't have to reinvent the wheel, right? Use what you have and implement the function that you need to, okay? So while we have used K-maps and QM till last week, this is one of, again, a very important skill you're learning in DD, right? DD doesn't necessarily mean that everything has to be implemented as gates. You have to start from the truth table and do gates, right? We'll talk about a few. So what we're talking about today are called as MSI, right? Just like LSI, VLSI, very large scale integration. These are medium scale integration chips. And so we'll talk. So that's what we're doing. So we're doing the adder. Now we'll talk about the comparator next, and then we'll do decoders, encoders, muxes, right? And this week's labs will give you an idea as to how to use them. These are very powerful tools and used almost in all digital design. So anytime you pick up an architecture textbook or anytime you're going to go into a microprocessor class next semester, right? This is where you'll start implementing. You won't start implementing with truth table and K-maps. You'd rather say, okay, let me just take a bunch of decoders, implement the function I need to implement, okay? So again, this is something that you need to start thinking about. So what you're learning in the class today and this week will be important to implement designs in real life, because all these chips you'll just buy on Amazon, plug them on the breadboard and start. So implementing a function is much easier when you have MSI chips as opposed to taking it gate by gate and doing it, okay? Obviously, if you're implementing, say you're NVIDIA and you're implementing the next AI chip, then obviously you want to go from the beginning, from transistor level. And that's because that is going to be your cheapest and going to have the highest profit. But for simple applications where you don't need the high speed or you don't need the high levels of integration, you can get away with just buying chips online. Okay. So the next MSI chip that we're going to look at is known as a magnitude comparator, right? And so so if I were to design an n-bit magnitude comparator, right? What do I want to do? I have two numbers, A and B, both of which are n bits. And I have three outputs from this chip, an A greater than B output, an A less than B output, and an A equal to B output, right? So I want to basically have a module which, if I send in two n-bit numbers into it, it has three outputs and it tells me which one is the greater number, which is the lesser number, or which is equal, right? So again, this kind of now helps you bring logic. So now when you have a comparator, then when you want to implement a subtractor that we did previously, you can figure out, should I take the two's complement of the first number or the second number, how to define a negative number, etc., right? So if you were to do it in K-map, right? So if I were to do it in K-map, how many inputs do I need to consider? So if I'm taking two n-bit numbers, how many inputs will I have? So if I have to write the truth table for this function, how many inputs and how many input outputs are we talking about?
2 to the power n minus 1.
So we have two n inputs, right?
As a
A is
sign.
n bits, A is n bits, and B is n bits. So here we are not worried about sign, right? We are just looking at the n bits. So suppose I'm doing a 4-bit comparator, I'm going to look at two 4-bit numbers, right? So the number of inputs I have is 8, two 4-bit numbers, right? So similarly, when I have n bits, I'm comparing the two n-bit numbers. So the total number of inputs I have is 2n, right? And three outputs, right? So if I do K-map, I have to worry about 2 to the power of 2n min terms, right, in the K-map. So instead, obviously, this is not the most efficient way of implementing, because this means you have to run a software to logic minimize and all that. So can we think of a better way to implement it? Okay, so let's do a simple case. Let's talk about two numbers. I have two numbers A and B made up of 4 bits each, right? So I have two numbers A and B made up of 4 bits each. Again, this is your MSB, that's your LSB. Similarly, this is your MSB, that's your LSB. Okay. So now let's think about the logic as to how do you implement this hierarchically. Okay, which means what logic we're designing here should be able to be implemented. If I increase the number to any number of bits, it should logically flow as to how do I just change the chip design, right? So if I have two numbers, so how do I start? Where would I start? Would I start at the MSB or LSB? So again, remember what we're trying to do is we're now going to go down to bit by bit, right? So what we're saying is, if A3 is equal to 1 and B3 is equal to 0, then we know that A is greater than B. And if A3 is equal to 0 and B3 is equal to 1, then we know that B is greater than A, right? So the first thing I have to do is that I'll first compare the MSBs, right? If the MSBs already give me the answer, I don't need to do any more processing. From the MSB itself, it will tell me exactly which one is greater or lesser. I need to move to the second MSB only when A3 is equal to B3. So when A3 is equal to B3, then move to the next MSB. So again, what we're doing is we are going bit by bit. So remember, in the adder, we started at the LSB and moved this way, right? Whereas in the comparator, I'm going to start at the MSB and move towards the LSB. Right? So what I'm going to do is I'm going to figure out if it's 1-0 or 0-1, then I know I can quickly tell whether A is greater than B or B is greater than B. And I need to move to the next bit only when equality exists. So let's first define, how do you identify equality? Yeah, is it XOR? So again, guys, remember, right now we're only doing magnitude. Don't worry about the sign convention. For sign convention, you'll have to think of a different way of implementing. Here I'm just doing magnitude comparator. So what is the equality condition? How do I, so what I want? I want to define a function x3 which goes high when a3 is equal to b3. So what is the Boolean expression for x3? X
X1.
naught, perfect, right? So it is a3, or you can write this as the min term 0 and 3, right? So this is the equality condition. So if I have to write the Boolean function for this, now let's write the Boolean function for is a greater than b. Let's without doing a truth table, let's write this function. So I will say a is greater than b, right? If A3 B3 bar, right? So A3 B3 bar is going to identify this condition, right? That is A3 B3 bar will be high only when A3 is 1 and B3 is 0, right? So I will say A is greater than B if A3 is 1 and B3 is 0, or A3 and B3 are equal and A2 is greater than B2. Okay, what I'm doing here in the second term is I'm saying that, okay, I will go to the second term only when my first two, my MSBs are equal. So that's when X3 is high, right? When X3 is high, then I'll compare the next highest MSB, which is A2 and B2. And again, if A2 is 1 and B2 is 0, then I will make the call that A is greater than B. If not, so if both are equal, then I will look at the next highest. And finally, so this would be my expression for the logic expression if A is greater than B. Again, what am I doing? My first term is just comparing the two MSBs, right? And I'm saying that if the MSB of A is greater than the MSB of B, again, life becomes simple here because we're dealing with binaries, right? So it's 1 and 0. So A3 B3 prime is just is going high when A3 is 1 and B3 is 0, right? So if that is already true, then I don't need to worry about the rest. Now I'll go to the next term only when these two are equal. So at that point, this term goes to 0. If A3 and B3 are equal, this term goes to 0. What you're left with is X3 being high. Then you look at the next um, two MSBs, right? And so on and so forth. So similarly, if I want to define the other expression, how would I write this? What would be the first term of this expression? So the first term of this expression is going to be A3 prime B3. So this is identifying the combination 0, 1, right? Again, if this is not true, then I look for equivalence and then I look at the next highest bit. Similarly, X3, X2, A1 bar, B1 plus X3, X2, X1, A0 bar, B0, right? So this is going to be my output for A less than B. And so for the third output, which is A is equal to B, what would it be? What would be the Boolean function for us A equal to B? Correct. Simple, right? So it's X3, X2, X1, X0. So it's a 4-input AND gate, which is taking all your equivalence functions and ANDing them together. So A is equal to B is going to be true only when each and every bit is matching, right? So again, remember, if you write this in English, it becomes very easy to write the Boolean expression, right? So here we can get the minimized expression without really doing K-maps or anything like that. All we're doing here is just writing the logical or trying to just interpret what is given to you in English and then writing the expression as is, right? So this is how you'd implement this circuit. So what do you want to do? So when you want to implement the circuit, you need to implement the X functions, right? Or the equality functions. So what you do is these will be your intermediate functions that you will implement, right? And these can be implemented with a simple XNOR circuit, right? So now what you see here is that this logic can be extended to like 8 bits now, right? 8 bits, you can either extend it as one big fat. So again, let me ask you a question. Let's talk about these terms. One, if A3 and B3, sorry, if both A and B bits arrive at time t equal to 0, right? Which term will be generated first? Or which term needs to go to less number of gates, right? All I'm doing is let's take this is a great, sorry. Let's look at this is A greater than B term, right? It is made up of four terms, right? Four product terms, 1, 2, 3, 4, say. So which product term will be generated first? One comes first, right? Right. Good. Good. And why is that? That is because that has the least number of gates to go through. So you should now be able to imagine how this circuit would have looked like, right? So what you see is that the first bit comes through and then the next one comes in, right? So here that also helps you with this design. So it's very quick. You don't have to wait for the other inputs to tumble in. because once A3 prime B3 is ready, if that is true, already sent the signal out. So in that sense also, this is a nice implementation because it lends itself to an implementation which naturally is makes a decision fast, right? So in the case, again, normally when you design a combinator circuit, you'll wait for all of them to be generated and you'll say that is your worst case delay, right? So remember that when I say worst case delay of this circuit, the worst case delay of the circuit will be the total time taken to generate this function, right? Which has to go through it has to go through multiple stages here and then go through this four input OR gate and finally go to this is A greater than B function, right? But what we see is that the output starts to come in early. So again, you see, again, we're not going to do this in this class, but what you begin to see is sometimes you don't need to wait for the worst case delay. If you are smart enough, if you can design a circuit which is smart, then you can play tricks like this to make your circuit faster, right? Again, this is not what is expected from you in this class, but I'm trying to get you guys to think that you don't need to necessarily follow rules, right? As long as you're aware of what risks you're taking, and if your project is okay with that risk, be a risk taker and ensure that you design a system which is most optimal, right? Because this will also save you power. Remember, if you can make a decision with just one term, it will also save you less power because then you can shut off this decision making immediately once I made the decision. Because then I can say, I don't care about the rest. This decision comes, so I'll shut off the power for this chip because I don't want to burn any more power, right? So, for example, if A3 prime B3 is high, then I already make the decision that this is true, right? And then I don't need to wait for this. So then I can say that I can shut off the power to this chip once I make the decision with A3 prime B3 and not worry about the rest of the terms, right? So again, these are simple ways by which you will optimize a system like this so as to reduce power, get maximum speed. Okay? But again, in this class, if I tell you what is worst case delay, you'll wait for all the bits to flip over and then you'll calculate the worst case delay. So implementation of this hopefully should be, so can you guys do the implementation by yourself or do you want me to draw the circuit diagram? It's a pretty lousy circuit diagram, right? All you have to do is implement these things using gates. So I'm hoping that that's something you guys can do. Okay, so again, remember how the magnitude comparator looks like. So this is going to be the block diagram of the magnitude comparator. So let's call it a 4-bit comparator. So it has 3 outputs, A greater than B, A less than B, A equal to B. Okay, and it is going to have 2 4-bit inputs, right? A and B. So again, remember this has no, and again, as I told you, sometimes you can have an enable signal. So we'll talk about enables in the next, if not in this class, in the next class on at 12 o'clock. So again, remember this has no, it's a pure magnitude comparator, right? So it has no information whether you're dealing with negative numbers, positive numbers, anything of that sort. It is simply going to compare 2 bits and it's going to compare 2 binary numbers and it's going to tell you which one is greater, which one is lesser. Now, obviously, if you want this to figure out if it's a negative number or a positive number, no, all that logic, then based on these outputs, you have to start making those decisions, right? So in a circuit, suppose you want to define do you want to find which number is positive, which number is negative, then you will have to send it through a 4-bit comparator. We know that the negative number will be in a 2's complement form, so its MSB is going to be always a 1 as opposed to a positive number which will have an MSB of 0. So I can, one thing is send it directly into a 4-bit comparator and do that. But I also know if it's a positive number and negative number, why should I use a 4-bit comparator, right? I can directly use just AN and BN, AN minus 1 and BN minus 1, and say that, if for A to be a positive number, or rather no, sorry, B is a negative number, I can say that is equal to A3 prime B3 or AN prime as prime BN, right? So this means that this function implements if b is a negative. So you don't need to use a comparator when you have to do simple things like finding out if a number is negative or positive. Using a comparator is going to take area on a breadboard, and it's probably going to be a waste of space, right? And you might spend energy on this comparator which is not needed. So for doing simple things like finding if a number is positive or negative, you don't need to push it into a comparator. But on the other hand, suppose you want to come find out which among two numbers is greater or lesser, then you have to compare all 4 bits. In that case, you would use a comparator. Okay. So again, just because you have a comparator, don't use it. Use it when you think there is a need for it. You should start to, again, the reason I'm bringing all this up is because this is a design class, right? So design is not following a certain procedure, but rather trying to think whether it's needed or not. Can I get away with a simpler design? Right. So that should always be at the back of your mind whenever you're doing anything in digital design. Do I need this? Put in components only when you absolutely are convinced that they are required. If you can implement them simply, use the simple implementation. Okay. So one thing you guys can do, it's a good exercise. So implement using gates. Implement this previous function using gates, and then the answer is in your textbook. And if you want to do it by yourself, you can do it and send it to me. I can help you uh, check if it's right or wrong. Again, when you implement using gates, you can use any gate you want, any gate, any number of inputs. So really no restriction on your design. Just go crazy. Yes, Akhilesh, you're right. If you don't need A, you can just use Bn minus one. I'm sorry, you're correct. But suppose I want to find if A is positive and B is negative, right? If I want to do some logic with a subtractor, and if I want to find if A is positive and B is negative, then I can use that. You're right. If B is only negative, then directly Bn minus one tells you that, right? So Bn minus one is high, you know it's a negative number. Otherwise, it's a positive number. Thank you. Okay. Any questions on the comparator? Okay, so if there are no questions on the comparator, let's look at the next MSI component, which is a very, very, very important component. This is extremely important because this is used. I think this is one of the most used MSI components across any digital system, and it's called a decoder, right? And why is so? Let me first tell you what is the input output diagram of the decoder, and then we'll look at some applications. So a decoder, you sometimes think of a decoder as n cross 2 power n. So in the most generic case, a decoder is thought of as an n cross 2 power n system, which means that it has n inputs and 2 power n outputs. So if I look at a so in the generic case, I can think of this as it is an n input. So this is an n cross 2n decoder. And this has 2 power n outputs. So if I number them 0, it all goes to 2 power n minus 1. Right? So you'll see sometimes people quote things like 3 cross 8 decoder or 4 cross 16 decoder. Or sometimes it's written as 3 is to 8, 4 is to 16. Right? Always remember it's of the form n cross 2 power n. So what is the function of the decoder? The function of the decoder is at any point of time in the decoder, right? Only one of the outputs is high. Which output is high is determined by the input, right? For example, in the 3 cross 8 decoder, let's look at a simple 3 cross 8 decoder. A 3 cross 8 decoder consists of A2, A1, A0. Let's right, and there are 8 outputs: D0, D1 to D7. So if the input term is 1, then D1 goes high, right? So depending on what A3, depending on what um, depending on what A3, A2, A1, A0 are, right? That particular D M will go high, right? So if my input is a 2, then D2 will go high, right? If my input is a 3, D3 will go high. So what you're seeing is basically, depending on what the input term is, that particular line in the decoder goes high. So what this becomes very, so I'll give you a good example of this. This is commonly used when you want to do address decoding. So think about a memory. You guys have done CP1, right? So you have a pointer. A pointer is nothing but an address to a memory location, right? And memory has to be addressed. So every memory will have a particular enable signal, right? So suppose I want to access a certain memory, right? You can think about the memory as connected to the output lines of the decoder, right? So if you think about this decoder, each of this decoder line will go to some memory cell, right? And so when you want to address a certain memory cell, you will send in an address to this decoder, right? And this decoder will raise only the signal to that particular memory, right? So suppose this memory has some address, say H. Let's look at a very simple H, let's say HA. Let's look at a 4 is to 16. So 4 is to 16 decoder means that it takes an input of 4 bits and gives an output of 16 outputs, where the line will go high when that particular line is called. So when I have HA, for example's address, if my address is A, then the 10th line in the output is going to go high, and that is going to enable the memory connected to the 10th line. And so once I enable that, then I can call out the um, data from that memory. So decoders are used very, very commonly in designs, especially in memory. So I think towards the end of the class, we'll do memory decoding. And it's there and right in the name. We say memory decoding, and that's basically used to decode the address. When you want to access a certain memory in the system, you'll use its address, and that address is decoded using a decoder. Okay. So how would you implement this in circuit design? Let's think about. Um, Let me ask you a simple question first. Let's think about a 3 to 8 decoder, right? So what I'm saying is that DM goes high when, suppose I call this input term as A, right? When A is equal to M, correct? So D0 will go high when the when the decimal value of A is 0, right? D2 will go high when the decimal value of A is 2. So what you see is DM goes high only when A is equal to 1, else DM is 0, right? So what can you say about the logical expressions of D0 to D7? Correct, very good. So this is nothing but the minterm. So what you're seeing is the decoder outputs are minterms. So if you want to design a circuit, it's very simple. You have to take an AND gate and NOT gates, and you can design the circuit for the decoder, right? So decoder is essentially made up of AND and NOT gates. For example, suppose I want to design D0. D0 refers to the minterm M0, right? And M0 is given by A2 bar, A1 bar, A0 bar, right? This is the expression for D0. Similarly, to think of D4, D4 is given by M4, and M4 is nothing but 100. So it's given by A2, A1 bar, A0 bar, right? So if you think of designing a 3 to 8 decoder, you need to have 3 inverters and 8 3 input AND gates, right? Right. So how would you design this? Very simple. You take A2, A1, A0, and using these you can create their inverted outputs, right? So I can create, so these are my A2 prime, A1 prime, and A0 prime, right? And so if I want to implement D0, I'll pull these 3 signals out and send it into an AND gate, and this is my D0, right? Similarly, I can design all the 8 minterms, right? By pulling in the right signals into the 3 inputs. So I can design an entire decoder using AND gates. Now, on the other hand, so this kind of a decoder where output goes high for select line is called as an active high decoder, right? That is, the output goes high, otherwise it's a zero. So it's called an active high decoder. In the market, many a times you get what is known as an active low decoder. So the low decoder is made up of the same implementation, but instead, let me just draw, instead of this, I would send it through an AND gate. So if I use an active low decoder, the way I draw the circuit diagram for that is the way, again, so this is an important convention you guys need to learn, is whenever we talk about active low inputs or outputs, we normally bubble them. So when you bubble this output, it means that this is an active low, right? And so now again, this is a 3-input gate. So this is taking a 3-input and this is giving. So now what is each of this output equal to? So again, remember this is normally high. So suppose I say DM is high always and goes to 0 when M is equal to A. So what kind of an output are we getting here? Max terms, very good. So which means now what you see is that, so this would be a max term, right? Because the max term is normally high and will go to 0 when you want to, when that particular term is highlighted. So what you see is that the active low decoder, so the active high decoder can give you min terms. The active low decoder gives you the complement of min terms, which are the max terms, right? And so decoders are very commonly also used to implement Boolean functions. And the advantage is that you can use one decoder and implement a lot of output functions, right? And the reason being because I can use this, for example, suppose I want to implement function x, which is f of, sigma m of whatever, say 0, 2, 3, 6. And I want to implement another function y, which is sigma of 1, 2, 7, right? So all I have to do is, how would I implement this using a decoder? Again, this is sigma of m, right? So I can use an active high decoder. And suppose I assume these are 3-input functions. So I'll take the 3 inputs. Remember, this is A2, A1, A0. I will give ABC. So let's assume A is your MSB and C is your LSB. So they have been fed into the decoder. This is a 3-to-8 decoder, right? And so again, I have my D0, D1, D2, D3, 4, 5, 6, and 7, right? Now I want to implement 0, 2, 3, 6. So all I do is take 0, pass it through an AND gate, and this is my function x. And similarly, when I want to implement the second function, I'll take 1. So let me,
So
I'll
would
take,
it be an OR gate or an AND gate?
sorry, OR gate. Yeah. Right. And similarly for the other one, I'll take 1, I'll take 2, and I'll take 7. Send it through an OR gate, and that's going to be my function y. So decoders find a use. One thing is for address decoding, as we just saw, but it's also used a lot to implement um, Boolean functions. So again, you see that this makes life much easy. So designing something off this would be much easier. So what do you think is the drawback of designing using decoders? What do you guys can think? Why don't people use this more often? Especially when you do NVIDIA. If you're NVIDIA, exactly, right? It's going to be slow because the decoder is going to implement it to 3-input AND gates, for example, in this case, and 3-input AND gates are going to be slow. So it is generating all the minterms, and if you don't really need, and normally you don't need all the minterms, right? So this is not an efficient, a power efficient or a speed efficient way of implementing the function, but it certainly is a easy customized way to do it, right? All you have to do is buy a decoder, buy a few gates, and you're done. So ease of implementation is very high in the case of a decoder implementation. The problem with this implementation, as you guys have all suggested, is that it's going to be slow and it's not going to be power efficient. So again, if you are Nvidia, if you are Apple, if you're designing a big chip, you will not use this technique. But if you're say Fisher Price and you're making toys, then this is a very easy way to do, because the cost of a chip on Amazon is less than a cent. So if you're going to make toys and don't want to spend a lot of money, or say you're building a robot, right, which you don't have the money to buy or customize your own chip, and you want to buy off the shelf components, then you'd use something like this, because that will be much easier. Now, one important function that you normally get with decoders is known as the enable. So what is the enable function? So let's look at a 2x4 decoder. Again, please remember, different books use different conventions. You'll sometimes see 2x4, you'll sometimes see 2x4. Right? So they all mean the same thing. Again, remember, a decoder takes n inputs and has 2 power n outputs, right? So keep that connection in mind. So what's the enable function? So if you think of a 2x4 decoder, a 2x4 decoder has 2 inputs and 4 outputs. So let's talk about the 2 inputs as x1 and x0, right? And the 4 outputs are D0, D1, D2, D3. Normally, and this is true on most of all chips, but this is the first time I'm introducing this concept, is that you have another input, and this is known as the enable input. So what is the enable input doing? So the enable input, from the word, from the name it suggests, the enable needs to be high for the outputs to be valid, right? That is, I will not trust the outputs of the decoder unless enable is high, right? So when you look at some of the data sheet, so go back, I'll post so if you go to Canvas, right, I've posted the link uh, to the in the lab section. I posted a link to a folder which contains all the data sheets that are normally used when if you were in the on campus and we're working in the labs. So go there today and look at the data sheet for a decoder, right, and normally has an enable function. So again, what does this enable function do? So enable needs to be high for the decoder to work, you can see. So if enable is 0, then I won't trust the outputs of decoder. So in other words, suppose I want to use this decoder, I'll first send a high signal on the enable, ensure that the decoder is turned on, and then I will start pulling the data from the output of the decoder. So remember that enable doesn't mean that the output will not be present. Enable is a signal which is used to ensure that what the output is coming is related to the input, right? The output logic value of the output may be rubbish until enable becomes high. So it doesn't mean that the output value doesn't exist. It might have zeros or ones in it, but you don't trust those values because the enable is down. So it might be values from the previous time enable was high, or it might be some junk values. Now that depends on how the chip has been designed, right? So again, whenever you want to look at the output of the decoder, always ensure that enable is high and then look at the output of the decoder. So if I want to design, shouldn't we have an enable output from the decoder for us to know the output? You can do that. Generally, we use enable basically if you have to shut down the chip or anything like that, right? So we use enable as a way to. Okay, good question. What I'm going to do is let Saransh is a very good question. I will let the class think about this question. We will talk about it at the 12 o'clock class. Okay. So those who are here, think about this question. What Saransh asked. So let's look at the truth table. Let's do something different now. Let's go back to our 2 weeks ago DD, and let's look at the truth table for this decoder. Right. So this decoder has 3 inputs: x1, x0, and e, and 4 outputs. So how would I write the one thing I will say is that if the enable is a high, if the enable is a 0, I don't care what the outputs are going to be. Right? I don't care what the inputs are. If enable is a 0, if I'm a smart designer, I will put this some number. So I'll say, okay, this should all be 0 if the enable is a high. If the enable is a low, then I'll say that the decoder will be output will be zero no matter what. Again, this is something I'm designing. When you buy chips from outside, it really depends on the data sheet. So always a good idea to go back and look at data sheets. So data sheet will clearly tell you what happens when the enable is not high. Right? And then we say, so only when enable is high will I have this decoder working. So I'll say when it's 0, 0, the only term that comes up is D0. When it is 0, 1, the only term that comes up is D1. 1, 0 is D2. So this goes as 0, 1, 0, 0. And D3 is this, right? So this is the truth table for this decoder. Right? So again, you see that if you want to implement this, you'll use an AND gate, right? And the enable function is your, when enable is 0, no matter whatever you do, the AND gate output is going to be a 0, right? So the implementation of this would essentially be, suppose you want to implement D0, D0 is going to be x1 prime, x0 prime, E, right? So only when enable is high will it become x1 prime, x0 prime. Otherwise, when enable is 0, the output of D0 is always going to be 0. So similarly, so what you will do here is, if you want to draw the circuit design for this will consist of 3 input AND gates and 4 of them, right? Because you want, for each of the 4 outputs, you want an AND gate, and the AND gate will be of this term, will be of the min term times enable. And one last thing I want to leave you with is, enable again can be active high or active low. And more often than not, you'll find chips which are active low. So what does active low mean? Again, remember, if I go back to the same 2x4 decoder, the way I'll define this is x1, this is x0. The enable will be shown like this. That is, this chip will work only when enable is 0. When enable is high, this chip will not work. Okay, do you guys understand? So keep in mind the difference between active. So this is saying that decoder works only when E is equal to 0. So it's an active low enable. So this chip, for it to work, you need to ensure that you bring your enable down to 0 and then send an x1, x0 so that you can decode them. Okay, so with that, I'll stop this lecture. I'll meet you guys again at 12 o'clock. I'll take the few questions that are there. So Saransha, shouldn't we have an enable out? So that we'll talk in the next class. Saksham, can enable be ANDed with outputs for us to know whether the it is? So yes, that's how you will implement this, right? So inside the chip, the enable is implemented in the AND function, right? So if you look at this expression tells you that the enable is included in the AND, right? And so this enable is going to kill the output if it's a 0, and will only give the valid output when enable is a 1. Because when enable is a 1, then essentially the enable output doesn't implement, the AND can be thought of as just the min term. So Harsh, good question. In active low, when we, if we are not using the chip most of the time, won't waste more power, as we need to connect it to power all the time, and that is very true. But what turns out normally is that, um, we'll talk about CMOS design in towards the end of this week. So CMOS design doesn't burn power when you have connected supply. CMOS design burns power only when you're switching. So CMOS, which is the most common design technique, CMOS is normally a switching sensitive design. That is, CMOS will burn power only when we switch the circuit. And so what happens is that generally we design enable signals such that the ones are easy to generate than the zeros. So in terms of noise and everything, it's easy to make a 1 than it's easier than 0. So 0 is generally more predictive than a 1. And that's the reason why normally when you're doing these enable signals, you use a 0, because when you're sending a 0, you're sure you're sending a 0. The problem with CMOS design and a lot of chips that you'll buy from the market would be that the enable signal It's very easy to generate a 1. So the noise margin for the 1 is much wider than the noise margin for 0. And so therefore, whenever we use enable signals, we use a 0 because it is hard to generate a 0. So if you have generated a 0, it means that you intended to enable that particular chip, right? And so that's why we use a 0. Good question.